and then I touched upon the challenges in development and deployment. Then I touched upon some basic concepts like Heisenberg uncertainty principle, then mutually unbiased basis, then no cloning theorem. Then I covered the BB84 protocol. So today I will cover mainly two protocols. First, in the first half, that is called differential phase reference protocols. So along under which that there are two protocols. One is called coherent one-way and or cow, and the other one is called differential phase shift or DPS. So in these two protocols, I will also explain how the secure key generation happens through a detailed animation. Then I will touch upon a multiplex QKD solution. What is its advantage? Why it is? How it is done. Then I will focus some of the CDOT solutions and some educational QKD solutions that may be beneficial for some of the faculties if they intend to establish a lab in future for quantum communications. So going forward, so as I told yesterday, there are under discrete variable protocols, there is a subset that is called distributed phase reference protocols. So distributed phase reference means here we check the phase relation between two consecutive pulses. So how do we check this? Check this relation? So that will be clear in the subsequent slides. So first protocol is coherent one-way or COW QKD. So as I told, this is a discrete variable protocol, and again this is a prepare and measure type of protocol. So as I told yesterday, prepare and measure means Alice prepares some quantum states, it sends to Bob, and Bob will measure this quantum state. And yesterday also I touched upon the basic devices or equipments that is there inside the Alice and Bob, like lasers, intensity modulator. So today you will get a good feel like how these components are interconnected within Alice and Bob nodes. So for coherent one-way, so this is like in BB84, our degree of freedom was polarization, right? So we are encoding the states using either horizontal or vertical polarization or diagonal or anti-diagonal polarization. So we had two bases. One was rectilinear basis. In the rectilinear basis, we had two orthogonal states like horizontal and vertical. And in the diagonal basis, we had two orthogonal states, diagonal and in the diagonal basis, there was two orthogonal states like diagonal and anti-diagonal. In the case of coherent one-way, the degree of freedom is called time bin. So here, the secret key is generated by measuring the time of arrival at Bob. So we decode in such a way that there are two time slots. One is called early and the other one is called late. And either for zeros and ones, the pulse will be either in the early or in the late time slot. And if photon is there in both the time slot, that is considered as a decoy sequence. Okay, so here in case of coherent one, the decoy sequence amplitude is not different. Only thing is that the photon is there in the both the time slots. So going forward, just take a look at how Alice node operates. So in Alice node, we have a continuous wave laser. So this continuous wave laser is a very narrow line width stable laser that we need. Typically, it is around 50 nanometer. Then we have an intensity modulator. So yesterday I told that this intensity modulator is basically a lithium niobate based intensity modulator. And along with this intensity modulator, there will be its control circuit like the modulator bias controller and the RF driver. Okay. And then there is a QRNG. So QRNG stands for quantum random number generator. So there is a chip that generates quantum random number. It feeds to an FPGA, and then ultimately this FPGA drives that intensity modulator through an RF driver in between. That is not shown in this diagram, but there is always an RF driver because this intensity modulator requires a higher voltage of the order of 6 to 7 voltage, 7 volt. So that's how this Alice operates. And then there is an attenuator. So this attenuator also I talked yesterday. This is a variable optical attenuator that is done to minimize the number of photon in a mean photon number of photon per pulse. Okay, so why it is required? Because we can't send more than one photon per pulse. Now, how the encoding is done? So as I told, there are two time slots. There are two time slots. One is early and one is late. So if the photon is there in the green time slot, that is the late time slot, we can encode as bit 0. And if there is a bit 1 from the QRNG, we have the photon in the early time slot, and the next time slot, the late time slot, is vacuum. Vacuum means there is nothing. So this time slot will go as a vacuum. And if the photon is there in the both the time slot, we encode as decoy. So that's how the encoding is done. This is our convention. You can revert the convention like bit 1 can be 0 mu, bit 0 can be mu 0, like that also. So this is only the convention, but for bit 0 and 1, only the early and late position changes. So if in case in this convention, the photon is there in the late time slot, so that's why it's called bit 0. That's our convention. And if the photon is there in the early time slot, it's called bit 1. and vice versa. And in case of decoy, the photon is there in both the time slots. So as I told, here the degree of freedom is the time slot or the time beam. Now these states are prepared in a random, because the quantum random number source will prepare some random bit pattern, zeros and ones. Based on that sequence, we will prepare a random sequence of these pulses. Okay, so this will be like this. So here you can see that this is a one pulse, and this dotted line is the time interval boundary. So you can see that this is again a bit zero, then it is I think it is again zero, it is one, and then this is the decoy sequence, right? There are two are green. Okay, so that's how it is being sent over a quantum channel, that may be an optical fiber, to a bob. Again, now see what is there inside the bob. Okay, so I think Alice part is clear. So this is the internal constituents of Alice node for coherent one-way protocol. Now in the bob node, we have again we have the same FPGA, and the thing is that in the bob we have two detectors, and they are single photon avalanche diode based detector. You can use this is as this photo is for the field deployable solution, so we are using the single photon avalanche diode based single photon detectors, but you can also use SNSPD like the superconducting nanowire detectors. So here what is happening, the pulses are coming and there is an optical splitter. So this is a passive device. So its purpose is that it divides the power in a 90:10 ratio. So 90% of the power it will go in this arm, and 10% of the power will go in this arm. Now out of this 90% power that will go in this arm, that will be detected as click in the SPAD 1 or the detector 1. So this line will contribute to generation of secure keys. Okay, so if I detect, suppose in the SPAD 1 we detect in time slot some in time slot 0 we detect at early, at time slot, so this is a time slot, this dotted boundary is a time slot. So suppose in time slot 0 we detect late, in time slot 1 we detect in late again, and then time slot 2 we detect in early, like that. So that's how we can detect whether we have received 0 or 1. That is, this detector 1 will contribute for generation of keys. Now 10% of the pulse will come to this arm, and there is a delay line interferometer is here. Okay, so the purpose of delay line interferometer is that it will cause an interference between the consecutive pulses where there is a photon. Okay, so there is a photon, you can see that there will be an interference, and this delay line interferometer is there, so it will delay one pulse and there will be an interference. And at the output of the delay line interferometer we have placed another detector. Now here comes up questions that if you see the architecture of delay line interferometer, you will see that there is two ports. One is constructive port, one is destructive port. Now there are two implementations of coherent one way. In one implementation they use two detectors, one in the constructive arm, one in destructive arm. But here in our implementation we use only one detector that is placed in the destructive arm, so that all these decoy pulses should interfere constructively. But if there is an if, that should that should go, some interference will go to the destructive port. So that's how we check how much is the if is there, whether it is there or not. So that's how we can check whether if is there or not. So there is a paper from Walenta that specifies how we can place that detector, and we can calculate the visibility using a single detector other than using two detectors in the delay line interferometer. So this arm is called the monitoring line, and this arm is responsible for generation of the keys. Okay, so based on these clicks in this detector, we can determine whether there is some eavesdropping is there in the quantum channel or not. So the parameter that is responsible for this detector, that is called a visibility. So checking that interference visibility, we can determine whether there is eve or not. So typical value should be more than 90-95%. But if there is some eavesdropping or there is some hacking activity taking place in the channel, then this visibility will go down. Okay, and so it is, I think it is clear now. So 90% of the pulse will come here, so that will contribute to generation of secure keys, either zeros and ones, and the other 10% that will come here, if there are decoy sequence, that will contribute to generation of the visibility parameter. Now the question comes, suppose we need to generate keys only based on these zeros and ones. So sometimes it will happen that this decoy state will also come here, so during the post processing we'll discard that. Similarly, it may happen that in this arm 10% arm, some zeros and ones pulses will also come, so that we need to discard, because only we need to consider here the decoy states that will contribute to ultimately generation of the interference visibility. Okay, so that's how this coherent one way or COW protocol works in a fiber based setup. Now If there is any query, please let me know in the chat so that I can address that. Okay, someone has asked that how do we get a single photon from a laser source? Okay, so the single photon, as I told yesterday, I think that there is not a very good quality single photon available commercially that have a very high fidelity and good repetition rate. So presently, what we do is that we generate weak coherent pulse. So weak coherent pulse means we attenuate a laser, then so that laser is a coherent source, and after attenuating it becomes a weak coherent pulse. So that's why it's called. So it is a continuous wave narrow linewidth laser, then we are attenuating it. Okay, so that's how it is called weak coherent pulse. So all this implementation is based on weak coherent pulse, because there is no single photon source that is of very high repetition rate that is available as of now in commercially. Okay, the other questions was yeah, the other questions was why do we use FPGA? Okay, so why do we use FPGA? Because we need the FPGA because we need to send the control signals. So we need some processor or controller to control these items. So FPGA is basically the heart of this system. FPGA is basically heart of the system, because this detector will click, then this FPGA registers this click. The classical channel is again connected between these FPGAs. Okay, so that's how this system is working. So FPGA is required because that works as a heart. All this QKD protocol that is implemented using RTL logic is everything is implemented in the FPGA. All these items, laser, intensity modulator, splitter, delay line interferometer, everything is like everything is a optical component. FPGA and is the electrical counterpart. So it is interfacing with this optical component and it is controlling those and receiving the data from the single photon detectors. Okay. Okay. So any other query, please let me know. Okay. Okay. So I think the coherent 1A protocol is okay. Then I will proceed to differential phase shift or DPS protocol. Okay. So in coherent 1A, the degree of freedom was time bin. As I told, in BB84, the degree of freedom was polarization. So in this differential phases, the degree of freedom will be phase. So here you will change the phase of the photons. Okay. So this architecture is similar to coherent one way, but there is slight difference. So if you see this diagram, then it will be clear. So you can see that here. So you can see that here we have again we have a continuous wave laser that should be of narrow line width. Then we have a lithium niobate based intensity modulator that is driven by FPGA through an intermediate RF driver that is not shown in the diagram. And then we have a phase modulator. So the phase modulator is again a lithium niobate based device. Its role is to modulate these states either in 0 or pi. So why do we require intensity modulator? Because the laser that is a continuous wave, so that will generate a constant laser power. Then we need an intensity modulator to generate the pulse. So these are the pulse, and based on the data from the random source, random number source, we will modulate these states in either 0 phase or pi phase. So if the QRNG output is 0, we will not modulate anything. But if the QRNG output is 1, we will modulate this pulse as pi phase. Okay, and then we'll attenuate it so that the mean photon number is less than 1. Okay, so for coherent one way, the mean photon number is typically 0.5, and for differential phase shift protocol, the mean photon number is typically 0.2. Okay, so that's how the protocol is designed. And these two protocols are inherently secure from the photon number splitting attack. Okay, so in this DPS protocol, we do not require any decoy state. It is inherently secure. So how it is secure, that you can come to know in the subsequent time. So this is the Bob Alice architecture, that there is a laser followed by an intensity modulator. So intensity modulator will prepare the pulses like this, and then phase modulator will be responsible for generation of the phases like 0 and pi. Okay, modulating the phases on these pulses. Okay, so typically this repetition rate is around 1 gigahertz, and then it is highly attenuated to have a mean photon count of on an average zero point 0.2. So what does mean photon number of zero point 0.2 means? So suppose you are sending 10 pulses over a channel, on an average 2 pulses will have some photons and remaining 8 pulses will not have anything, that will be vacuum. Okay, so that's how this works. Then again this pulse train will travel to quantum channel to bob. In the bob again we have a delay line interferometer. So this part is a delay line interferometer. So there is a 1 bit delay. This is the time period t and this is the 1 bit delay. So and in the output of this, here we are using two detectors. One is called detector 1 and detector 2. And now how this interference will happen, just follow these animations. So here you can see that we have these 4 pulses, that for example, then they will be delayed by 1 bit because there is a path delay of 1 bit here. Then they will interfere. So you can see that if they are interfered in the same phase, because here you can see that they are all both are in the zero phase, so they will interfere constructively. So the S pad in the constructive one will click, and when there is a pi phase difference, the S pad in the destructive one will click. And based on that you can understand that if there is a pi phase difference, this detector will click, so that we can consider that the qrng data that was sent from alice was 1. And if this spad 1 clicks, we can understand that the data that was sent from alice is 0. So so basically here both of these detectors are responsible for generation of the keys. In case of coherent one way, only one spad was being used for generation of key, and the other spad was used for checking the visibility or checking the presence of eve. But here both of these detector are being used to generate used for the generation of the keys. Okay, and again these clicks are then registered in a FPGA that will then process these clicks, and then the keys will be generated. So that will be, I'll cover in the subsequent slide. So here you can check that if there is some eavesdropping, then this phase relation will change, and that will reflect in some wrong clicks in this detector. So that will automatically increase your quantum bit error rate. And seeing that, you can understand that whether there is any eavesdropping in the channel or not. Okay, so that's how this differential phase shift protocol works. Okay, so please let me know if there is any query regarding this differential phase shift QKD. So if this is okay, then I will proceed to how the key is generated. I gave an overview for BB84 yesterday. So today I will show you an animation that will be more clear how the keys are being generated. So here you can see that if the consecutive bits are 0, then this detector will click, and if the bits are 1, then another detector will click, and these clicks will be registered in an FPGA. So this is basically working as the heart of this system, because that will actually implement this protocol. Okay, so someone is asking SPAD 1 and 2. Okay, so you can see that if in a delay line interferometer, there are two ports. One is responsible for constructive interference, and one is responsible for the destructive interference. Now this is a 1 bit delay line interferometer, and in this example we have four. We have taken only 4 pulses for clarity, so that we have 0 0 pi 0 sequence. So I delayed it by 1 bit. So 0 comes here, 0 comes here, pi comes here, and then this will interfere. So if this will interfere, so you can see that this pulse is having 0 phase, this pulse is also having 0 phase. So they are in same phase basically. So if they are in same phase, they will interfere constructively, and this SPAD 1 in the constructive arm will click. So if this splat clicks, so we can understand that they are in the same phase. So 0 was sent from alice. Similarly, if this splat clicks, so this is connected in the destructive arm. So 0 and pi, there is a pi phase difference, so they will clear, there will be a destructive interference. Splat 2 will click, and we can understand that then we can understand that 1 was sent from alice. So that's how 0, this detector clicks means 0 was sent, this detector clicks means 1 was sent. So that's how we can shift the key that based on the data sent by alice. Okay, so that's how these two detectors contribute to the generation of keys. Okay, now again I showed you this slide. This slide is same for both BB84 and coherent one way or DPS protocol. all these steps will be same. Like the first there will be classical channel authentication, qubit transmission and synchronization. Then we will get the raw key. Then there will be some error correction. Then there will be privacy amplification. Now today we have a good animation that will give some in-depth idea of how these steps are being done. Okay, so to go to that, just let me see if there is any other query. Okay, so SPAD is basically a single photon detectors, so avalanche diode based. So SPAD stands for single photon avalanche diode based single photon detectors. Okay. Okay, so there is just follow this key generation process. I think it will be clear. So, like how keys are generated in a QKD system using any protocol. So this will be for any prepare and measure type of protocol. This thing will be valid. Okay, so for example, let's take there are two nodes, Alice and Bob. Alice is acting as transmitter and Bob as receiver. So they are connected using one quantum channel and one classical channel. So once they power up, so they will do a classical channel authentication. Okay. So classical channel authentication means Alice will verify whether this is the actual Bob, and Bob will verify if this is the actual Alice. So it is done by an algorithm that I told yesterday that is called Poly 1305, and this will be based on a pre-shared key. So that will be factory program. So once the authentication is successful, then they will proceed for qubit transmission. If the authentication fails, that means Alice and Bob can't verify whether they are actually the legitimate party or not. The communication will not start, so it will abort. So key generation process would not proceed further. So for explanation, let's take a 30-bit sequence. So these 30-bit sequence are prepared by any random number source. It may be a quantum random number source, or it may be a true random number source. So this 30-bit pattern has been generated, and then these random bit pattern will be sent over quantum channel to Bob. Now for BB84, they will be encoded in polarization depending on whether it will be horizontal, vertical, or diagonal, anti-diagonal. For coherent one way, they will be encoded in time bins, early or late. And for differential phase shift, they will be encoded in phases like 0 and pi. So if there is 0, there will be 0 phase. For 1, there will be pi phase, like that. So depending on the protocol, only the encoding part will change, and similarly the decoding part will change, but the remaining steps will remain more or less same. So here we have taken 30 bits. They are sent over a quantum channel to Bob. Now every channel will have some loss, because if there is for fiber there will be around 0.2 dB per kilometer loss in the 1550 nanometer. So if there is loss, then there will be attenuation of power. Now we are sending very little power, like in the form of single photons. So we have taken 30 pulses. So out of those, I have, for example, I have taken 12 pulses have reached actually to Bob, because there is some loss. So the dashed area, the photon is absorbed in the fiber. And you can see that there are in two areas there is some red, because we sent 0, but due to some channel noise or the detector imperfection, this 0 has flipped to 1. Okay, so I sent 30, but ultimately 12 was received at the Bob end. Okay, so this is my first step of qubit transmission, and we have assumed that these Alice and Bob are synchronized, so they have a clear idea which is time slot 0, which time corresponds to time slot 1. So they are properly synchronized. And we took a 30-bit pattern, we encoded it in either phase or time bin or polarization, and then we send it over the quantum channel. And in the Bob side, we received them, but ultimately we sent 30, but we, unfortunately, due to the channel loss, we received only 12, because the other photons got lost in the channel due to the absorption by the channel, and some photons were received in error because there is some channel noise or there is some detector imperfections. Okay, so we sent 30, we received 12. Okay, but this 12 is random. Alice does not know which 12 is received by Bob, whether it is 12 or whether it is 10. So Alice has no idea how many has been received and which a particular time slot data has been received to Bob. So qubit transmission phase is over. Once this phase is over, then the role of quantum channel ends, and every subsequent process will be carried over the classical channel. Okay. So next step is Bob will disclose the time values of these bits. Like if you see that it has not received anything in T1, it has received something in T2, again nothing has been received in T3, and it has received something at T4. So it will reveal these time values like T2, T4, T6 and T7. Only this time value, it will not reveal whether it has received 1 or it has received 0. So you can see that Bob is disclosing through quantum classical channel only the time slots at which it has received something, not the actual value, like whether it has received or 0 or 1, it is not disclosing. It is disclosing only the time values at which time it has received something. There is any click at Bob's detectors. Okay, so it is revealing the time slots, and Alice is already having the records because Alice had sent this bit pattern, and it is they are synchronized. So Alice note at which time he has sent something. So then Alice will discard remaining 18 and keep the corresponding bit pattern corresponding to these 12 time slots. So now Alice is having a bit pattern, Bob is having the similar bit pattern, but due to error they are not identical. You can see that in the red position, here it is 0, here it is 1. So there is some error. But they are now left with 12 bits, and Alice came to know that at which time slot Bob has received something. So they have bit pattern, but that is not identical. Okay, so the shifting or the filtering process is over here. So they are left with 12 bits of raw key. Now they again the classical channel will come into picture, and this time Bob will choose a subset of these values. So there are 12 bits with Bob, and Bob will choose a subset. So random, typically this value is around 3%. So suppose they will disclose 3% of bits with time slot and value. So they will choose a 3% among these subset, and they will disclose the time values and the value of bit 0 and 1. Okay, so they will disclose both. So for example, if I take one bit, so that may be, say, for T1 it will be T and the value will be 1. Okay, so for T1 it will be 1, or if I take randomly takes is for example T3, so T3 and 1, like that. So Bob will disclose only for the subsets, that is typically 3%, that is called the disclose rate. So they will disclose this value to Alice, and then Alice has this value stored, so they will compare the QBR, quantum bit error rate. Okay, so that's how these things operates. Now the thing is that these in the example I have taken only one bit, so one bit value that is chosen randomly from this pattern, and then Alice computes this QBR, and each protocol has a QBR threshold. So as I told yesterday that BB84 has a threshold of 11%, coherent one way and differential phase shift has around 5% threshold. So if that quantum bit error rate in those disclosed bit is less than the threshold, then we will proceed, otherwise we will abort this process. Because if the quantum bit error rate is more than the threshold, then there is some eavesdropping in the channel, or the channel is not secure, or there may be some equipment malfunction, so we should not generate the keys. Okay, so that's why it is always always done that if the QBR is less than the threshold, this threshold comes from the theoretical security analysis. So if the QBR is less than the threshold, then we proceed for the further post processing steps. Okay, so suppose we have taken here the 12 bits, one bit was disclosed, so QBR is less than 5%, for example. Let's take that. So we are left with 11 bits. We are left with 11 bits, and again you can see that in the 11 bits also there may be some error remaining, because in the undisclosed bits also there may be some error remaining, so they are not again identical. Okay, so we are left with 11 bits, but they are not identical. Okay, so these steps, whatever I am telling, it is same for BB84 coherent on or differential phase shift. Only thing is that for BB84 here, for the time slots, along with time slot we need to disclose the basis as well. So yesterday I told about the rectilinear basis and diagonal basis for BB84. So for BB84 we need to disclose the time slot plus basis, but for coherent one way and differential phase shift there is only one basis, so we need to disclose only the time slots. Okay, so only these things will change, but the remaining subsequent step will be remain same for all these three protocols. Okay, so now we are left with 11 bits. Then but they are not identical due to the channel noise, so we need to perform a error correction process. So typically, as I told yesterday, that the error correction process that is used is low density parity check, and there are some other algorithms like cascade is also used in some implementations. So after this error checking process, these bit pattern available with Alice and bit pattern available with Bob are identical. Okay, so we can use this bit pattern for as a secure key, but the issue is that during this error correction, this parity information is exchanged over the classical channel. And as I told, the classical channel can be listened by Eve. So there is no security in the classical channel per se. Or Eve can listen, it will not it cannot modify, because this channel is authenticated, but it can listen this in communication, and he can get an idea of the what is the secure key that is being generated. So some information may get leaked to Eve. So to prevent that, we do a privacy amplification process. So that is basically we compress this bit pattern. Says here it was 11 bits, so we have compressed it to 2 bits. then we will get the actual final secure key. So that is actually used for secure key. Now if we actually run this protocol multiple times, then this key will be keep on generating and it will be stored in your memory. So this, then if some router or encryptor request for key, then we can supply this key. So this is actually this is the final step. So this is after this privacy amplification process, we are left with the secret key. So here you can see that in the quantum key distribution process, we sent some raw data from Alice to Bob, and the secret key was generated at both the ends simultaneously. So key in its raw actual form was never sent in the channel. We sent some data in the channels. So we started with 30 bits, 12 bits was received. Then we disclosed the time slots and the basis. Then we got disclosed some to check the quantum bit error rate. If the quantum bit error rate is less than the threshold, then we proceed with error corrections. And after the errors are corrected, then we perform the privacy amplification to avoid the information leakage to Eve. So after the privacy amplification step, we are left with the secure key. Okay, so this all you can see that only the quantum channel comes into picture during the qubit transmission phase, and all other subsequent operations like this error correction, privacy amplification, everything takes place using the classical channel. Okay, so quantum channel role ends in after this stage, and then everything takes place in the classical channel. Okay, so just please let me know in the chat if there is any queries regarding this process, because this is how the keys are generated in any algorithm. Okay, so someone is asking why 11 bits, because I have taken an example here. So I have taken an example that we started with 30 bits, 12 bits were received, and 1 bit I disclosed here in this stage. I disclose only 1 bit. So typical value is 3% here. So typical value is 3%. So for the example, I have taken only 1 bit I have disclosed. That time slot, say for example T3 plus 1 and 1. So I disclose the time slot and the value for only 1 bit. So 12 bits, so it is disclosed. So we cannot use it for further processing, because this disclose is done in the classical channel and if can listen this. So to avoid that, we discarded that. So from 12 we came down to 11. We are using the classical channel not for reference, but we are using the classical channel for the post processing steps like the error correction and the privacy amplification and this shifting purpose. Okay, so next slide I will cover the multiplexed QKD system. So yesterday I told that the performance of QKD system will be best when we are using a dark fiber for the quantum channel. So dark fiber means there is no other signal in the in that optical fiber. But the thing is that the use of dark fiber is very costly, and in the field you may not get all the time a dark fiber dedicated for your quantum channel. So to avoid that, there is a concept called multiplexing, multiplex QKD. So here what happens, we use wavelength division multiplexings. So in one wavelength, say suppose in 1550 nanometer your quantum channel is there, and other data signals and the quantum and the QKD classical channel may be in the other wavelength. Say for example 1551 will be your classical channel, and this data wavelength can be say in the 1555 nanometer. So in one fiber, different wavelengths will carry different signals. So that's how this wavelength division multiplexing operates. So quantum channel is unidirectional. So from Alice to Bob, you can see that in this example that we implemented, there are three signals. One is called the quantum channel, QKD quantum channel. One is the classical channel, QKD classical channel, from Alice to Bob direction. And there is a 100G encrypted data that is from Alice to Bob. So there are from Alice to Bob, there is three wavelengths, three signals. And from Bob to Alice direction, there are only two signals, because quantum channel is unidirectional. So from the Bob to Alice direction, there is 100G traffic plus the classical channel receive detections. Okay, so that's how this multiplex system operates. So you can, if you are interested, you can refer to this paper where we have implemented this multiplex QKD system over a 50-kilometer distance. But the basic concept is that in the dark fiber based implementation, we can go up to a much higher loss, say up to say 30 dB of fiber loss. But due to the leakage or noise from these classical signals that are very high power, and the quantum signals are of very low power, so that will keep on corrupting due to the nonlinear effects, say for example Raman scattering and all this. So we cannot go much very far distance using this multiplex QKD system. So that is a challenge, but it is suitable for short distance of deployment. So we have done till 50-kilometer, and we got some good QBR performance and in this setup. So in this setup, the basic challenge is the distance. So multiplexing saves your dark fiber cost, but the thing is that the distance get limited due to the noise. That is, that the noise primarily is from the signal leakage from the classical signal and the non-linear effects like Raman scattering and all this. Okay. Now, coming to the solutions that we have developed for QKD, so this is only for your reference that we have come up with this coherent one-way and differential phase shift QKD systems. So this is our Alice and Bob box. And yesterday I told that to increase the distance, we use a trusted relay in between. So relay is basically cascading the two links. One will be Alice Bob, then another will be Alice Bob. So here you can see that we have developed a relay node here. So this relay node basically caters both Alice and Bob functionality. So it reduce the single box solution will reduce your size, weight, and power consumption. That is called the swap. So here it happens that the Bob will be connected to the Alice part of this node, and this Alice will be connected to the Bob part of this node. So that's how this single box is helpful for elongating the distance of the link. And for suppose this topology Alice to Bob supports say up to 150 kilometer, then this if we use this three node, we can go up to 150 plus 150, so that will be 300 kilometers. So this is the relay node also we have developed, Alice and Bob also we have developed. And this is actually the quantum key distribution system graphical user interface. So here you can see that this is the quantum bit error rate. I told you that the 5% is the threshold limit. So typically it is in the system that the screenshot that I took had it is 3%. This is the DPS protocol, and the key rate is around 2 kbps. And you can see that the real-time variation of the quantum bit error rate and the secure key rates. So this graphical user interface is actually is good for monitoring your system. You can control different parameters. You can configure the systems using a single web-based applications. So this comes along with the system. You just need to plug a laptop with the system, and you can access the system and you can check the performance. So this is the typical parameters. You can visit our website as well. You can get a details brochure there. So as I told, there are two protocols: differential phase shift and coherent one-way. QBR threshold is 5%, and we support 2 kbps key rate for differential phase shift and 1 kbps key rate for coherent one-way. Now you may ask that why the key rate for coherent one-way is less, because you know that for coherent one-way only one detector is being used for key generation. One detector is being used for eavesdropping detection, and for DPS both the detectors contribute to your key generation. So that's why the protocol is designed in such a way that for a given loss, that in the DPS the key rate will be double. So in the 23 dB value that comes from the TEC GR recommendation, but we can support up to 30 dB of loss. So and the quantum channel wavelength that we are using is around 1550 nanometer, that is the C band. We can transfer the key over any Ethernet or USB interface. And I told you that there is a limitation for QKD systems, that they need to be operated in an air conditioned environment, because the single photon detectors can't really operate beyond a certain temperature. So that's how the operating temperature is from 10 to 25 degrees centigrade. The detector type that is typically used is a SPAD based, single photon avalanche diode based, and it works on standard 230 volt 50 hertz supply. Okay, and you can also mount it in a 19-inch telecom rack. These boxes can be mounted on a 19-inch telecom rack. Now these are some of the deployments and field trials that we conducted, and we started in December 2021 with that field trial in the Indian Army network. Then actually after that we deployed this setup in a commercial order basis to multiple educational institutes. So we given the setup to JP Institute of Information Technology in Noida in 2022. Then we gave this system to DY Patil University in Mumbai in June 2024. One system was installed in ARNet India, and it was connected with the metro area quantum access network, or MACAN, of IIT Madras. So it was helpful for testing the interoperability between two QKD links, one from IIT Madras and one from CDOT. And in last year in February also we completed the installation in Netaji Subhas University of Technology in Delhi. So multiple educational institutes have procured our systems, and they are using it for different academic research purposes. They have published some good papers. Apart from that, one link is operational between the Sanchar Bhavan, that is the Department of Telecom, and NIC headquarters in CGO complex in Delhi. And all the traffic between these two offices are encrypted using the keys that are being generated by C.QKD system. So C.QKD system generates the key, it supplies to a router. then this router actually does the encryption, and this link is end-to-end encrypted. And again, we need some filter in Indian Air Force and Indian Army. And we have some TOT partners like transfer of technology partners, so they actually manufacture systems for us for any large scale deployment. So recently there was a tender from scientific analysis group of DRDO. So our technology partners they bid for the tender, and they secured order for two QKD links that was deployed in September 2025. And after that they also another secured another order from DRDO solid state physical laboratory for another link in November 2025. And recently we have received another purchase order from Mahindra University Hyderabad for deployment of one QKD link. So these are all our deployments and field trials. Now these are the some of the recognition letters that we have received from different educational institutes who have used our system, and they have recommended. You can see that Professor Animan Patak has published some papers also. The reference is given here using our systems, and this letter is from DY Patel, and this is from the ARNET. These are some of the patents that we have granted, and these are some of the research papers. So this paper is for that multiplex UKD system that I was discussing. Our systems also got some awards, so like Aegis Gahambrel Award and Technology Software Awards, LCN Awards. Then I talked about the transfer of technology. So for small scale deployment, we deploy ourselves, but for large scale commercial order, we have four transfer of technology partners. One of them is a PSU, Electronics Corporation of India Limited, and there are three private sector companies using two startups, Skytel Alpha and Chip Spirit. And as I told, this new age instrument, they have secured two tenders from DRDO. One they have already deployed, and another they are going to deploy in the solid state physical laboratory. Okay. Now I'll briefly touch upon the educational QKD solutions. So actually the thing is that in India, all of you are aware that a national quantum mission has been launched, and IIT Madras and CDOT is responsible for the quantum communication hub. And then DST has always come in collaboration with AICT. They have also rolled out a quantum technology UG minor curriculum. So they have come out with a good syllabus for the UG quantum technologies course, and also there was a funding calls from DST for quantum technology labs. So they are to fund some universities to establish quantum technology labs, and it is at par with the global trends. Like in other major economies, also they are also heavily investing in different quantum education and initiatives. And it is also very imperative that we need a very good skilled quantum workforce, and that is seen as a strategic national capability building, because every country is now needs to secure your own digital infrastructure from the quantum threats. So that's why we need to secure our cyber security infrastructure, banking networks, defense and strategic networks. And for that we need good quality theory as well as practical insights. So for that we customized our solution to make it more cost effective for the educational sectors. So it is a completely indigenous and solution with long term supports, and it is compliant with the AICT's curriculum also. And we can support multiple experiments that will give us in hand experience of how the keys are being actually generated. So we support three protocols, DPS and cow, and we customize this coherent one-way protocol called coherent one-way slim. So this is basically a cost effective version, so that it fits in the educational budget. And if someone procures this coherent one-way slim version, that can also be later upgraded at an additional cost to either coherent one-way or differential phase shifts. The hardware is designed in such a way that they are upgradable. And also we have a solution that is called eave simulator, so that I will cover in the subsequent slide, that will simulate the effects of eavesdropping. So you can see the effects, like if there is an eavesdropping in the channel, how your system will react. So that will also give an insight to the researchers. So these systems are very beneficial for all the researchers, students and faculties, so they can perform good experiments, they can get a practical insight, they can publish papers, and then they can understand the concept through an hands-on experience. So this is the Eve simulator that I was talking. So Eve simulator basically is a device that goes in the quantum channel. So here we are simulating three attacks. One is called the photon number splitting attack. The other one is the spurious signal injection, and the third one is the fiber tempering. So what happens in photon number splitting attack? So we are simulating the effects of this attack. So we are not actually launching this attack, because performing this attack is a very difficult task. So we are actually simulating the effects, and we are seeing that whether your quantum system is actually resistant to these attacks or not. So in PNS attack, what happens if there is a multi-photon pulse? If generally takes one photon, keeps you to it, and the extra photon it sends to Bob. Okay, so to prevent that, generally it is recommended that you keep the mean photon number less than one. So but if when the if does this, if it counts the photon, then it disturb the phase relation between the pulses. So to simulate that, we are using a random phase modulator inside this box, and we randomly change the phase. And if you use this, if you enable the PNS attack using this if simulator unit, you will see that the visibility in the quadrant 1 will go down, and the quantum bit error rate in the differential phase shift will go up. So that's how you can detect that your system is immune to this attack. So it can detect any such type of attack, and there is a proof of quantumness of this system. So that's how this can be validated. Similarly, there is an attack called Trojan horse. So in Trojan horse attack, some spurious lights is injected from outside to the QKD nodes. So here we launch a spurious signal power, and again it will reflect as a increase in your quantum bit error rates. Similarly, if someone is trying to tamper on your fiber to capture some signals, so your ultimately your fiber loss will increase. So we have put a variable optical attenuator inside this if simulator box, and if you enable this attack, then the actual loss of the quantum channel will go up, and again it will reflect as a increase in quantum bit error rate. So this solution is very useful for demonstrating the quantumness of your any quantum key distribution system, whether it is actually a quantum system or not. So you can verify using this system, and this is also helpful for some education purpose. And we have also deployed it in RNet Chennai, and this scientific analysis group of DRDO has also procured it through our TOT partner. Okay. So before I go to the next session, so just let me know if there is any query regarding this distributed phase reference protocol. Then I will start with the entangle based protocols. So I can take some questions on that on this. Avinash Sharma is asking which simulation software is used here. In which you are talking of any simulation software? Where are you asking? We this is actually a practical system. No simulation software we are using. Regarding what you are asking for the simulation software? Then someone is asking, can you please help me understand whatever you have shown is operational for regular secure communication based on terrestrial fiber-based channel? Yes, it is actually operational, and it is deployed in fiber, deployed in the field using optical fiber, because showed you that one link is deployed between Sanchar Bhavan and NIC headquarter, that is carrying the live traffic. And we have given this setup to this Alice and Bob nodes to multiple universities. They have set up labs using our coherent one-way slim version, and scientific analysis group DRDO has also procured our QKD systems. How we will choose the phase shift in DPS protocol? Sir, ma'am, actually this in DPS protocol there is a QRNG source that I showed you in that diagram. Yeah, so there is a QRNG source here, and this QRNG will produce a random bit pattern of zeros and ones. So if for some time the QRNG is 0, then there is no phase modulation. If the QRNG bit is 1 for some time interval, the if optical pulse will be modulated by pi. So the QRNG determines whether the this random number basically determines whether the phase modulation will be 0 or pi. So this is random based on the data provided by this random number source. Please let me know if any other query is there. Yeah, it is actually a very good questions, like what are the limitations of fiber-based QKD? The limitation of the fiber-based QKD is basically the distance. So fiber-based QKD is advantageous for that it can operate 24 cross 7, because the free space QKT has a limitation that it cannot operate in a foggy weather or in very daylight time, because there may be some solar noise. But the fiber based QKT can operate 24/7. But the present issue is that we cannot really go beyond say typically 150 kilometer in a good fiber or 200 kilometer in a good fiber. But the issue is that beyond it is very costly in that sense. So if we can go up to 1,000 kilometer in a single span, that will be very cost effective, because for suppose for going from Delhi to Chennai, we need to place these trusted repeaters every say around 80 to 90 kilometers, because in field the fibers are not that of very good quality and they will be very lossy. So that's why we need to have these trusted nodes in between, and the cost goes up, because in all the trusted node areas we need to have air conditioning, we need to maintain those nodes when there may be electricity outage and everything. So that's why this limitation is coming from the distance limitation of this of the fiber based QKT. In image encryption, the bit stream is related to the source image. So in that condition, how QRNG generates the phase? QRNG is not generating any phase. QRNG is only generating zeros and ones. It is a random number source. It is like similar like to your pseudo random sequence. So the pseudo random sequence is basically a bit pattern, zeros and ones. But QRNG is a more secure randomness source. So it will produce a string of zeros and ones, and based on that random number we can modulate the phase modulator, either zero phase or pi phase. So QRNG is only acting as a source of randomness, and based on this random number we will modulate the phase. Would you explain Trojan horse attack? So in Trojan horse attack, the what happens, one light source is transmitted, that is injected to the channel, mainly to the Alice, and then some light will get reflected back from the Alice, and then this Eve analyzes that reflected light to gain some information of the internal states of the quantum nodes. Okay, so that's how the Trojan horse attack works. And the mechanism to avoid it is using an optical isolator in the inputs. But that optical isolator is also have some power limitation. But the only countermeasure to avoid Trojan horse attack is using an optical isolator. So that optical isolator will only allow light to come out from Alice towards the channel, but no light will go inside Alice from the channel. So that's how we can prevent the Trojan horse attack. But if this countermeasure is not there, so someone can launch an laser, high power laser from the quantum channel towards this encoding device, and based on the reflected light they can guess some state of the encoding device that will ultimately reveal some information of the secret key that is being generated. Okay, so that's how the Trojan horse attack works. So in our simulator we have a high power we have a laser. So that laser will inject it, and then you can see the effect on the in the GUI. So the quantum channel in all the protocol is used for secure communication only, else we can use the classical channel for everything. Ma'am, the quantum channel is used for transmitting the qubits from Alice to Bob, and the classical channel is being used for these post processing steps like the shifting, error correction and privacy amplifications. Okay, so quantum channel purpose is only to send the qubits from Alice to Bob, and based on these received qubits at Bob, both Alice and Bob will generate the keys. Okay, so keys are not sent directly over the channel, only some data is sent in the form of qubits in the quantum channel. Then the role of classical channel also comes, and then the key is generated. So the role of quantum channel is to send the qubits in the form of single photons from Alice to Bob. We can't just use the classical channel, because if we use the classical channel then the quantumness property will vanish, because classical channel is like classical communication. Then there will be no quantum property, because in quantum communication the thing is that if you measure the states in the quantum channel then they will destroy, and then they will be reflected as a quantum bit error rate. So if we use classical channel that we are currently using, currently all our all our communications are classical, we are using the classical communication only at present. If we use classical channel, then quantum there will be no quantum property. We can't use Heisenberg uncertainty principle, we can't use no cloning theorem. That only works in the quantum domain. Encrypted information is sent through classical channel. Yes, encrypted information is sent through classical. You can send. Yeah. All our present communication is being carried out in the classical channel. So QKD is generating the keys, and based on those keys, you can encrypt your data using any router, and that will be sent over any communication channel. That is basically classical. Only the thing is that we are using the quantum channel for transmitting the qubits. Everything else is classical, and your present communication is also called the classical communication. That is already there. You may have a fiber broadband at your home. That is also classical communication. Okay, so should I proceed to the next step, that is the entanglement based QKD protocols, if it is okay with everyone? Okay, so till now we are focusing on prepare and measure based QKD protocols, where we have two nodes, Alice and Bob. So Alice was preparing some quantum states, Bob was measuring it, and based on that the key was being generated. Now there is another type of QKD protocols, that is called the entangle based QKD protocols, and this entangle based QKD protocol is considered to be more secure than any prepare and measure type of QKD protocols. Under entangle based QKD protocols, there are two major protocols. One is the BBM 92 protocol, and another one is called the E91 protocols. So I will, before going to that protocol, I will discuss some time on the what is actually a quantum entanglement is, because without understanding the quantum entanglement in some way, you can't actually understand the BBM 92 or E91 protocol. And again, yesterday I talked about that basis, rectilinear and diagonal basis. So in BB84, so these concept will again be valid for these two protocols. Okay. Then, if the time permits, I will show some diagrams of the QKD networks as per the ITUT standards. Okay. So going forward, we need there are some drawbacks of the prepare and measure protocols, because they are simple to implement, but the drawback is that, as I told, there is no commercial single photon sources as of now. So we use the weak coherent pulses. So we used a highly attenuated laser sources that sometimes may contain multi-photon pulse. So if there is a multi-photon pulse, so if can take one photon to it and send the other photon to Bob, so the photon number splitting attack might happen. Okay. Again, you have seen that we are using a random number source in Alice. So that's this random number source is basically using is being used to generate the states. It then, based on that random number source, we can using either phase modulation, or we are using that in current one, it is deciding the time slots, or in BB84 this is deciding the polarization value. Okay. So this random number source is required. We are not using, we don't have a true single photon source, so we are using weak coherent pulses. And as I told, they can be vulnerable to side channel attacks. Okay. So that's how these are the drawbacks of the prepare and measure protocol. So quantum mechanics is secure from the theoretical aspect, but there may be side channel attack, like someone pointed out, Trojan horse attack. So this type of attack may be there in case of prepare and measure protocols, because someone can launch some signals from outside and he can gain some information that is from the reflected signal. Okay. So these are some drawbacks of the prepare and measure protocols. So to rescue, there is this protocol called entangle based QKD protocol. So here, apart from Alice and Bob, we have another additional node, that is called the Charlie. Okay. So earlier we are dealing with two nodes, Alice and Bob, but here we will deal with three nodes, Alice, Bob, and Charlie. So the role will change here. So earlier Alice was the transmitter, Bob was the receiver. Here what will happen? Charlie will be the transmitter, and both Alice and Bob will be the receiver. Okay. So Charlie contains an entangled photon source. So entanglement photon source, they produce a photon pair that are correlated. Okay. So how the correlation happens, so that I will discuss in the subsequent slide. So these entangled states make this protocol very much secure due to the entanglement monogamy. So what does it mean by entanglement monogamy? Monogamy means if a particle is entangled with, suppose there are two particles and they are entangled. So if they are entangled completely, that is called maximally entangled, then there cannot be any correlation with any third party. So if there are two particles, they are entangled between Alice and Bob, so there will be no correlation with the any third party or Eve. So that's why it is called the entanglement monogamy. So it, one particle cannot have maximally entangled with two particles. It will be only maximally entangled with one particle. So that is why this term is called monogamy. So the examples are BBM 92 and E91 protocol, as I told. Now, before going to these protocols, I want to highlight that what is the difference between quantum entanglement and classical correlation. Okay, so we have a source. So it is generating an entanglement pair. So one part of the pair will go to Alice and the other part will go to Bob. Now, what happens with quantum entanglement? So suppose we have a source there, and this is a quantum source. So they are generating an entanglement pair. So one goes to Alice, other part goes to Bob. Okay. Now if I measure at time zero, okay. So at if I measure at time zero, for example, I am measuring at a certain time. Then if I get an Alice in this a vertically polarized light, that is the green line, then immediately we'll know that at Bob we'll get a horizontally polarized light. But if I measure at some other times, for example, I measure at T1, then if I may get this blue line, that is an anti-diagonally polarized light at Alice, and we will immediately know that the light at the Bob is diagonally polarized. Okay, similarly, if at another time if I get an horizontally polarized light at Alice, we will immediately know that we have at Bob we have got a vertically polarized light. So that's how the quantum entanglement works. So this depending on the time of this measurement, the outcome will change. But if I measure at Alice end, we will immediately know what is the value at Bob end. So they are correlated already. But this is different from the classical correlation. But in what happens in classical correlation, it here you can see that the outcome is dependent on the time. So at t equal to 0 and t equal to t1 or t equal to t2, the outcome is random, but they are correlated. So if Alice is horizontal, Bob will be vertical. Alice is vertical, Bob will be horizontal, like that. But in case of classical correlation, if I measure at different times, the outcome will be similar. So it may be happen that if Alice is horizontal at T1, then it will be horizontal at T2. It may be horizontal at T3 also. So like that. So it is always the values will be same. So it is deterministic, but here this value is random, but they are correlated between Alice and Bob. So there is a subtle difference between quantum entanglement and classical correlation. So in quantum entanglement, what is happening? The outcomes are random, but if I measure at Alice, suppose at t equal to 0, we are measuring at Alice and it is coming as vertically polarized light. So we immediately know that at Bob it will be horizontally polarized light. Okay. But in case of classical correlation, the measurement outcome is not time dependent. So if Alice we get a vertically polarized light, say at time t1, at t2 also we'll get the same thing. Okay. So that's the subtle difference between classical correlation and quantum entanglement. But the thing is that how do we actually quantify whether it is actually a classical correlation or it is a quantum entanglement? So for that there is a called Bell test. Now, before going to Bell test, so just to see like what is quantum entanglement. So there is a system A and B. So they are entangled, and by chance, if we measure A, the state of B is immediately defilled. Similarly, if we measure B, the state of A is immediately refilled. So they are not, they can't be represented as a single state, but they can be represented only as a together. We cannot describe them as a standalone system. They are not independent of each other. We cannot describe them independently. So we only need to describe the system as a whole. That's how the concept of quantum entanglement is. So we can write this system as like this. If there are two such systems, so this is the entangled state can be represented like this is the coefficient. And for suppose horizontal or vertically polarized light, we can write that horizontal plus vertical. So it means if we get a horizontally polarized light at Alice, we'll get a horizontally polarized light at Bob. But if we get a vertically polarized light at Alice, then also will get a vertically polarized light at Bob. So that's how this entanglement is represented of a maximally entangled states. Then I'll go to this Bell CHS violation. So before going that, if there is any doubt regarding the entanglement phenomena, please let me know. There. Before that, then I will go to this thing. Is there any doubt regarding the entanglement phenomena? Okay. Okay. So the thing is that when this quantum mechanics was discussed in the 1900s, Then this Einstein told that this quantum mechanics is incomplete and there may be some hidden variables, and they called this entanglement phenomena as a spooky action at a distance. Why spooky action at a distance? Because Einstein told that this quantum mechanics cannot be complete because it violates the local realism. Okay, so what is local realism? So there is a term called locality. So locality means if that outcomes at one location are not influenced instantly by distant events. So in quantum entanglement, what is happening? If I measure at Alice and we get a vertically polarized light, we immediately know that at Bob end we will get a horizontally polarized light, like that. So we there is a no, so it can't happen unless there is some information exchange that is faster than light, because these changes are this is very instantaneous. And then these two particles can be very far that there is no, actually there is no communication that is faster than light. So the correlation is like that. So he conclude that this violates the local realism, so this quantum mechanics is not complete. Then that this concept of realism is that it states that physical properties exist with definite values even if we don't measure. So suppose there is a ball, and if we don't measure but its mass is there, but in quantum mechanics if we don't measure, we don't know what will be the value. Like if we measure at Alice but immediately we don't know the value at Bob. So that's why this violates the property of local realism. So to give to that, John Bell in 1964 came up with a theory that he proposed a mathematical inequality that, and he derived that if the quantum system violates this inequality, then we can clarify that there is no local realism and actually this violation is there. Okay, so then CHSH is a four scientists. The names are mentioned here. They came up with actually an experiment to show that how to verify that Bell inequality. Okay, so there is a parameter that is called the Bell CHSS parameter. So for classical correlation, these values are less than 2, and for quantum mechanics, this violation can go up to 2 root 2. Okay, so this CHSS value is less than equal to 2 for classical and less than equal to 2 root 2 for quantum mechanical correlation or entanglements. Okay, so this experimental violation confirm that there is some non-local correlation. Okay, so that's how the entanglement works. Okay, so to summarize, so in Einstein told that because there are three scientists, Einstein, Podolsky, and Rosen, they confirmed in 1935. They claimed that this quantum mechanics is incomplete, and this is a spooky action at a distance, and there may be some hidden variables. That's why they told that quantum mechanics is incomplete. But in 1964, Bales came up with a theory that is the Bales inequality equation, and he told that there is no hidden variables. And later on in 1969, CHSs, the four scientists, they came up with an actual experiment based on that Bell's theory that if this parameter is less than 2 for classical correlation and less than 2 root 2 for quantum mechanical correlations. Okay, so that's how this system works, and quantum mechanics violates this local realism. So what is that local realism that I told? Is that locality means there is no faster than light effects, and reality means if you don't measure, the physical property still exists, but quantum mechanics will violate this parameter, violate this concept of local realism. Okay, now how to test this CHSS inequality? So this is the actual experimental setup of CHSS inequality. So here we have an entanglement source at Charlie. Okay, so that will generate an entanglement pairs. So one part of the pair will be sent to Alice and the other part will be sent to Bob. Okay, and at Bob and at Alice we have a PR. PR stands for the polarization rotator. Okay, so and then after the polarization rotator we have a polarization beam splitter. So what is the purpose of fluorescent beam splitter? So if there is a photon light is coming here, so it will split the light into two orthogonally polarized part. Okay, so if a light is coming, so horizontal part will go here and vertical part will go here. Okay, but here we have a single entangled photon source, so it will come out with a photon pair. One photon will go here and one photon will go here. Okay, so the Alice and Bob setup is there, that they are identical to test this CHSS inequality. And as I told, for classical entanglement, classical correlation, classical systems, this S value will be less than 2, and for quantum states that can go up to 2 root 2. Okay, so this is the experimental setup. So here you can see that there are 4 single photon detectors. They are marked as A prime, B and B prime. and this polarization rotator can have some certain values. Okay, so just keep an idea of this diagram, that there is an entanglement photon source, then there is a polarization rotator, that this polarization purpose of this polarization rotator is to choose the measurement basis, at which basis we need to measurement. It can be horizontal, vertical, it can be some other degrees that I will say in the subsequent slide. Okay, then we have this measurement equipment, that is the single photon detectors connected with the polarization beam splitter. So this is the experimental setup of the CHSH inequality. Now how this S parameter is calculated? So this is the equation actually. So this is the equation, and you can see that from this equation, this alpha and beta values are given. So these are some fixed values. Alpha is 0, alpha dash is 45, so alpha is 0, alpha dash is 45, beta is 22.5, beta dash is 67.5. So these are the polarizer setting. Okay, so and for this, how to calculate this E alpha beta parameter? E alpha beta parameter is this equation, and as I told, A, B and A dash B dash is the detector numbers. So the NAB means the coincidence at detector A and detector B. So at a certain time, what is the coincident count at detector A and detector B? Similarly, A dash B dash A dash B. So we are basically calculating the coincidence between with this detector with this with this, A dash with B, and A dash with B dash. So these are the coincidence parameter, and from this equation we need to calculate the E values, E for alpha beta, and this alpha beta is basically the settings of this PR. What is at which angle? Alpha is for Alice, beta is for Bob. Okay, so we need to rotate the polarization rotator at a certain angle based on this alpha beta value. For example, we need to calculate E alpha beta. So alpha will be 0. So alpha, this polarization rotator will be placed at a 0 degree angle, and this will be kept at beta, that is 22.5 degree angle. So in that setup, we'll get E alpha beta, and how we'll get the value? Then we need to compute this coincidence values. AB stands for this detectors: SPD A, SPD B, SPD A with SPD B dash, SPD A dash with SPD B, and SPD A dash with SPD B dash. So that's how the equation will be calculated. And for this entangled state, we can prove that if this experiment is performed, then we will see that this S value will be higher than 2. That's the violation. Then this violation, actually there is a theoretical foundation for this, and if this violation is there, you can confirm that this is actually an entanglement phenomenon is there. So that's how this quantum entanglement is quantified using this Bell CHS violation experiment. Okay, so please let me know if there is any doubt in this part. Then I will go to the actual entanglement based bed protocol. So why do we perform this test? Because this test is will also be performed during the E91 protocol. So that's why I included this part in this session, because this will be a part of the E91 protocol. It is not used in BBM 92, but in 91 this Bell test will be done. So when I'll cover the 91 protocol, this will be again used. So if you have any doubt, just please let me know. Yes, yes, please tell what is the doubt. Yeah, explain the equation. Which equation you are talking about, Mr. Prahlad? Which equation we need to I need to explain? Actually, the thing is that in case of quantum entanglement, we have an entangled source. Then this entangled source, if we transfer these states at a very far distance, suppose one part is in Earth, another part is Mars, and if we measure the part at Earth, we immediately know what is the value of the part at Mars. Okay, so but there is no faster than light communication, and this correlation is such that if we know the value at Earth, we immediately know the value at Mars. Okay, so here that's why the violation of non-local correlation, this concept of non-local correlation comes, or the violation of the local realism concept. Okay, because each parameter that as I told in this slide, you can see that realism states that physical properties exist with definite values even if we don't measure it. Okay, so for example, if we have a ball and if we do not measure it, its mass will be there. You cannot measure, even if you don't measure, its mass will be there. For suppose the ball have a weight of 1 gram, even if you don't measure it, it will be 1 gram. But in case of quantum entanglement, if we measure at certain time, the value will be something. If we measure at another time, the value will be something. But we don't know actually that what will be the outcome. But if we measure one part, suppose we measure the entangled particle at Earth, then we immediately know what will be the value at the other part of this entangled pair at Mars. Okay, so that's how this violation comes. So it is a non-local correlation for the entanglement particle, and this and this non-locality can be confirmed using this theoretical foundation that was developed by Bell, and this experimental setup that was these four scientists, they have made this setup. They have a complete theoretical foundation, and then these experiments, then we need to calculate that S parameter, and this using that S parameter we'll get, if this value is more than 2, then this confirms that this inequality is violated, and then we confirm that this is an quantum entanglement. For classical source or classically correlated source, these things will not be violated. So it will be, the value will be S, the value of S will be less than equal to 2. That is mentioned here, not entangled or classical source. Okay, so that is a good question, how this entanglement pair is generated. Okay, so how these pairs are generated, there are many methods. So one of the common method is called spontaneous parametric down conversion, or SPDC. So there are some crystals, there are nonlinear crystals. So we give a palm signal into it, and then they generate entangled pairs. So there are three types of entanglement pair generation using that SPDC process. There are three types of SPDC process actually. So one is called type 0, type 1, or type 2. So in type 0, what happens if the your pump is horizontally polarized, then your there are two signals out, one signal in, that is the pump, one signal is called signal, and the other one is called idler. So one input, that is pump, two output, that will be signal and idler. Okay, so for example, we are giving a 775 nanometer signal to a nonlinear crystal, and we will get a 1550 nanometer output at two signal and idler. Okay, so they conserve the energy and they conserve the momentum, so these conditions will be satisfied. So that's why we hc by lambda, that is the energy. So if 775 nanometer is the input, 1550 nanometer will be the output for the two signal and idler. They can be others also, like, so if that equation is satisfied of that energy conservation. So one may be 1549, other may be 1548, depending on the how the equation is satisfied, but they need not be identical, like they need not be 1550 always. So that is one method. So in type 2 SPDC, there are two vertically, like if one particle is H, the other particle will be V. One particle is V, other particle will be H. So HV plus VH type of entangled particles will be generated in type 2 SPDC. So you can search that type 2 SPDC is a very common method for generating polarization entangled in source. So there are different crystals, one like BBO crystals or KTP crystals, and depending on the crystal that they operates in different wavelengths and different conditions, like the phase matching conditions and the this energy and momentum would be conserved. Then these entangled pairs should be generated. So that is the most common type of generating the entangled source. Spurious parametric down conversion. You can search on that, study how the entangled pairs are generated. And nowadays many commercial companies are generating entangled source. You can procure them using that SPDC properties. Some use SPDC type 2, some use some other types of SPDC like type 0, then they use some Sagnac interferometer to generate that for entangled states. So in type 0 SPDC, what happens? The output signal and idler, they are having the same polarization as the input. In type 1, they are vertical. Suppose the input is horizontal, the out signal and idler will be vertically polarized. So, and in case of type 2, what will happen? Output will be VH plus HV. So if one signal is V, idler will be H, and his idler is V, signal will be H, and vice versa, like that. So this entanglement photon source can be realized using spurious parametric down conversion using a nonlinear crystal. that can be a BB or KTP type of crystals. Okay. Now coming to BBM 92 QT protocol. So BBM 92 against this naming convention is coming from the inventors. So this is the BB is the same persons as the BB 84, that's Charles Bennett and Gilles Bassard, and the third person is the David Marmin. They proposed this protocol in 92, so that's why it is called BBM 92. And this is the initials of their name, and this is the year of the in which it was proposed. So how does it operate? So here we have an entangled photon source at Charlie. Then this Charlie will send this photon pair one part of photon pair to Alice and the other part to Bob, where they will measure. Okay, so suppose they are generating n photons, n pairs, so they will send to Alice and Bob, so they will get 2n bits. Okay, n pairs means 2n bits. Then they will use the, so before going to this flow chart, just focus on this truth table. So yesterday I talked about this horizontal rectilinear and diagonal basis. Okay, so this is our convention. So in rectilinear basis, vertically polarized light we are taking as 1, and horizontally polarized light we are taking as 0. Similarly, at diagonal basis, we are taking that anti-diagonally polarized light as 1 and diagonally polarized light as 0. So this is our convention. Okay, so there are two bases, rectilinear basis and diagonal basis. Okay, so again, so this Charlie, there is an entangled photon source at Charlie. It is generating that entangled states and it is sending to Alice and Bob. Okay, so if it generates n pairs, Alice and Bob will get total 2n bits. Okay, n pairs, so n is going to Alice, n is going to Bob, so total 2n bits. I think that is correct. Now they will choose this basis either rectilinear or diagonal at random. Okay, so there are two bases and there are two parties, Alice and Bob. So there will be 4 combinations. Okay, 4 combinations. How? Alice is choosing rectilinear, Bob is choosing rectilinear, RR. Alice is choosing diagonal, Bob is choosing diagonal, DD, RR, DD, DR, RD. Okay, so you are aware that there can be, if there is 2 states, there can be 4 combinations. Okay, in 2 parties. So this out of 4 these combinations, DD, RR, RD and DR, so they out of these, in case of only 2 there is a match. Okay, so that what are the 2? DD and RR. So only when Alice choose rectilinear, Bob choose rectilinear, there will be match, and Bob choose diagonal, Alice choose diagonal, there will be match. Others, there in other cases the basis is mismatched, so we cannot conclusively decode the state, as I told showed yesterday, that we need to match the basis in case that was in that I showed in case of BB84 yesterday. So basis in 50% time there will be match of basis, and 50% time we need to discard it. Okay, so we transfer 2n bits, and in 50% time there will be basis mismatch. So Alice has received n, Bob has received n. So out of that n by 2 will be discarded. So from 2n we will come up to n by 2 bits. Okay, so that is the 3 by 4, this 3 by 4 times of bits are lost. So from 2n bits we are coming to n by 2. Okay, because 50% time, they on an average 50% time there will be no basis match, so they will discard those. So they will be left with n by 2 bits. Now to evaluate QPR, so they will disclose 10% of bits. Okay, so from n by 2 they will disclose 10% of bits, so they will be left with another 9 by 20 n bits. Okay, so I think it is clear, because 10 means 10% will be disclosed, so 90% remains, so 90% of n by 2 is 90 n by 20. Okay, 9 n by 20 bits Alice and Bob will have. Then they will run privacy amplification and error correction process, and after that they will compress on an average about 50% of the compression they will apply. So after compressing 50%, it will happen 9n by 40. So that is roughly equal to 9n by 4, that is 9n by 36. Okay, so that's how they, with n pairs, they can generate about n by 4 bits of secure key using 50% privacy amplification. Okay, so just let me know if this process is clear, then I will these numbers are clear, then I will describe how this actually the states are being generated or the keys are being generated. Please let me know if there is any doubt in this mathematics.
So there is somebody saying to repeat the 4 states, probably the explanation.
Okay, Okay, so I'm repeating that. Okay, so there are two bases. Okay, that you will agree that there are two bases, rectilinear and diagonal, and there are two parties, Alice and Bob. Okay, so rectilinear I am telling as R, diagonal as D, and there are two parties, Alice and Bob. So they can choose at random this basis. So there are four combinations. So Alice choosing R, Bob's choosing R, Alice choosing D, Bob's choosing D, Alice choosing R, Bob choosing D, and Bob choosing Alice choosing D, Bob choosing R. So RR, DD, RD, DR. There are four combinations, right? And there is an entangled photon source at Charlie that is generating n pairs. So n bits will go to Alice, n bits will go to Bob. So there are total 2n bits. So out of these 2n cases, only 50% we will keep because Alice is having n bits, Bob is having n bits, and in only in 50% cases they can decode these states correctly because there will be basis match. So out of four states, RR, DD, DD, RR, out of four states, only in two cases there will be match. So 2 by 4 is 50%. So Alice is having n bits, right? So n bits, Alice is having n bits, so that n bits will become n by 2 because 50% time it is not matching. So from 2n there is a loss of 3 by 4. So from 2n we have come to n by 2. That's why the loss is coming. 3 by 4 times is loss. In that n by 2 bits, that is with Alice and Bob, they will disclose around 10% of bits, so that for checking the QBR, quantum bit error rate, and they will be left with 9n by 20 bits. Okay, so that is the 90% of it. N by 2 into 90% is 9n by 20 bits. So this QBR estimation, this disclose is same like that was done in prepare and measure case. And after that they will do error correction, and then they will do privacy amplification by having a 50% compression ratio. So if I compress this 9n by 20 bits by 50%, so it will become 9n by 40. So you can roughly that can be 9n by 36 or n by 4. Okay, so that is about n by 4. So that is that okay, or should I repeat again?
Somebody is also saying, could you explain error correction again?
Yeah, error correction, the thing is that while we are sending the states from from Charlie to Alice and Bob, so sometimes there is a channel. Okay, there is a channel in between. Alice and the Charlie is in the center, Alice and Bob are connected using a quantum channel. So in as it was there in the case of prepare and measure protocol, there always be there some noise in the channel. So when these entangled states are traveling and getting detected in the Alice and Bob, sometimes it may happen that Alice state and Bob state, they are not correlated due to the noise. They are entangled, but due to the noise they may register as something else. So suppose Alice is receiving H, Bob should also receive H, but due to the noise it is received as V. So that will be reflected as a QBR or noise. Okay, so to correct this mismatch, we need to perform this error correction algorithm that was earlier. That is the same as in the case of prepare and measure protocols. Error correction we need to do in both type of protocol, because during the transmission there will be some noise in the channel and some state will be registered as a wrong state. So H may become V, V may become H or something else. This is the limitation of your system, or that is the due to the noise. Anything can happen. So that's why this noise is there, and then noise will be always there. So QBR, there is a threshold. So if there are noises above that threshold, we cannot generate key. So this threshold is 11% for this protocol, and if it is less than the threshold, we can generate the keys. But error will be always there. So we need to correct those errors using LDPC or cascade type of algorithms. Okay. Okay, so I think no other query is there. So then I will show you this truth table. So here is an entangled source that is generating HH plus VV quantum states. Okay, entangled states. So HH plus VV means if Alice generates a if Alice gets a horizontal polarized light, Bob will also get horizontal polarized light. If Alice gets V, Bob will also get a vertically polarized light. Okay, so this is the meaning of these entangled states. Okay, so if Alice gets H, Bob will get H. If Alice gets V, Bob will also get a vertically polarized light. H means horizontal, V means vertically polarized light. Okay. Now there are two bases, rectilinear and diagonal basis. So if Alice and Bob both are choosing rectilinear basis, the first column, just see on the first column, Alice has received vertical, so Bob will also receive vertical. So they can assign the bit 1 here. This is from this truth table, 1 rectilinear and vertical. This is 1 is coming from here. then they can generate the key as 1. Okay. But if Alice chooses a rectilinear basis, the second column, but Bob chooses a diagonal basis, they cannot determine which state was received by sent by Charlie, because Alice will decode it as horizontal, Bob may decode it as diagonal. Okay. So this is inconclusive, so this state will be discarded. Similarly, the third column is also inconclusive, that will be discarded. In the fourth column, again this is similar to the first column, that is conclusive. In the fifth column, both of them has chosen diagonal basis, so Alice has determined that it is it is diagonal. Bob has also determined it as diagonal, so they can shift as 0. So these three columns will be used for key generation. Now in the fourth column, you can see that Alice has received diagonal, but Bob has received anti-diagonal. Okay, because as this is a HH plus VV source, so it and if there is a basis, if there is a diagonal basis and we send that H or V signals in it, sometimes we can get V diagonal, sometimes we can get anti-diagonal. Okay, so yesterday I told you the concept of basis. So if our state is generated using rectilinear basis, that is the case here because H and V, so H and V are in the rectilinear basis. So if we measure this in the diagonal basis, sometimes we can get diagonal, sometimes we can get anti-diagonal. So this has happened in the last column. So there is a state called HH, and we have Alice has measured it in diagonal basis. He has got diagonal, but Bob has got anti-diagonal. So it is perfectly okay because there is a 50% probability of getting these two. Okay, so somehow Alice, in this case Alice and Bob has got similar result, but in the last column they have not got similar result. So this is actually absolutely fine because there is a 50% probability when we are measuring a H state or a rectilinear basis state using the diagonal basis. Okay, so that's why in this case they are not able to generate keys because Bob will decide it at 1, Alice will decide it at 0. So that's why this will go for error checking. Okay, so that's how the system is working. So in these three bits, that will contribute to the secure key, and the remaining where the basis is not matching, that will be discarded. Okay, so that's how this BBM 92 protocol works. Okay, so it is similar to BB 84, but here the concept of basis is also here. But only thing is that here we have the single photon sources, that is the entangled source at the Charlie node, and Alice and Bob is working as the detectors, and only they can only generate the keys when the basis is matching. When the basis is not matching there, they are choosing this basis at random, this horizontal or rectilinear basis or the diagonal basis, they are choosing at random. So if the basis is not matching, they can't actually shift keys from that, so that need to be discarded. Okay, so only we need to focus on the green columns, and in the last column, as I told, in this case it had got a diagonal, it has got an anti-diagonal, so there is an error, so they need to discard it. So this error will be revealed during the post-processing steps. Okay, so this is the actual setup. There is an entanglement photon source at Charlie node. They are connected to Alice and Bob using the quantum channel. And for this post-processing steps, the classical channel is connected between Alice and Bob. Okay, so quantum channel is from Charlie to Alice and Charlie to Bob. Classical channel is between the Alice and Bob because they need to discuss what will be the basis and all this. They need to discuss these things for error correction and privacy amplification. But Charlie has no role in it. So Charlie is only a source, so it is only generating the quantum states, and it is sending to Alice and Bob. The final keys will be available with Alice and Bob. Charlie will not have any clue of the key that will be generated at last. Charlie is only acting as an entangled source. So please let me know if there is any more doubt in BBM 92, then I can proceed to E91. Can you please explain the matching of bases in sequence? How do they check basis state? Okay. So yesterday I told that basis matching is done during the classical post-processing steps. Okay. So when this entangled pair is generated, that will be sent to Alice and Bob. Okay. These entanglement states are generated at Charlie and sent to one part is sent to Alice, one part is sent to Bob. Then Alice and Bob will choose this basis rectilinear or diagonal at random. Okay, they will choose this basis at random, and when the choice of basis of Alice and Bob matches, only then we can generate the keys. So just I will show you the yesterday's slide. It will give you an idea. Once again for your clarity. Yeah. So I think there some people missed this part yesterday, so that's why I'm showing it again. So here we have a rectilinear basis. So we are assigning a vertically polarized light zero state here. So we have produced a vertically polarized light using a rectilinear basis, and if we measure it using a rectilinear basis, we can with 100% probability we can say that we have recovered the vertically polarized light. Okay, but if we have generated a vertically polarized light using rectilinear basis and we use a diagonal basis to recover it, we will never get vertically polarized light. This result will be either diagonally polarized light or anti-diagonally polarized light with 50% probability. Okay, so that is the case that was happening there. So because if we can divide this vertically polarized light electric field as cos 45 and sin 45 components, so they will have a 50-50 probability in each arm. Okay, so there will be two possibilities, either diagonally polarized light or anti-diagonally polarized light. So if there is a basis mismatch, we cannot recover the actual state with 100% fidelity. Okay, so that's why when the basis is not matched, they are discarded. So that this concept I described yesterday. So how the basis concept of basis works. So basis means there are two orthogonal states that represent a quantum state, quantum system. So in rectilinear basis, we will have horizontal and vertically polarized light. In diagonal basis, we will have a diagonally and anti-diagonally polarized light. So they are orthogonal, so that represent a total quantum system. But state generated in one basis cannot be perfectly decoded in another basis. So there is a 50% probability of getting detected as a diagonal and anti-diagonal. I think this is clear. I think it should be more clear now. Okay, I think it is now clear. Okay. So the basis information is exchanged after during the post processing through the classical channel. That's why the classical channel comes into picture. So once they receive some quantum state, they will discuss their choice of basis using the classical channel. So Alice will discard that, disclose that I have received, says at T0 I have chosen rectilinear basis, at T1 I have chosen diagonal basis, like that. So Bob can correlate with that. So they will discard that time intervals where they have chosen different basis. That is there from this truth table. At different, if the basis choice is different, no key will be generated. If the basis choice is same, then only they can proceed with generation of keys. And sometimes there may be errors due to the channel noise or due to the basis issues. Okay. Okay. Now in this protocol, the in BBM 92 protocol, we have assumed that this source is perfectly generating perfectly entangled state. Okay, we have not performed any check on the source. Okay, we have trusted this source that it will always produce perfect entangled state. There is no other issue. But E91 protocol is more secure in the sense that it performs a check on the source. So it will verify the source whether it is actually an entangled source or not using that Bell CHSH state that I showed earlier. Okay, so here the thing is that here Alice measurement basis and Bob measurement basis are different. Okay, so Alice will measure at three bases: 22.5 minus 22.5, 67.5 minus 67.5, 0 and 90. That is the rectilinear basis. Bob's basis are 0, 90 and 45 minus 45. So that is the diagonal basis. So you can see that only one basis is matching between Alice and Bob. That is the rectilinear basis 0, 90. Okay. So in other cases, there is basis mismatch, but these will contribute to the Bell CHSH test. So you can see that these degrees are the same that was there earlier in this equation. You can see that here we are having 0, 45, 22.5 and 67.5. Okay. So Bob has 22.5 and 67.5. Alice had 0 and 45. And these angles are the same. So these will be used for performing the Bell CHSH test. Okay. So here again the same thing happens. Charlie prepares a entangled source. Charlie has an entangled source and prepares an entangled pair, and it sends them to Alice and Bob through the quantum channel, that may be fiber or free space. Alice and Bob independently make their measurements at random basis. So these are the bases. So they will choose these bases at random and they will measure their states. After the measurement, the process, both Alice and Bob declare their basis choices through classical channel. Okay, it was same in the BBM92 protocol. After the measurement is done, they will discuss their basis, and they will generate keys only when their basis matches. That is the rectilinear basis or the 0 degree 90-degree angle. Okay, and rest of the measurement will go for checking the Bell's parameter for security of the protocol. Okay, so they will calculate this. So you can focus on this truth table. So again, we have a source that is generating HH plus VV, and then Alice is choosing these bases at random 090 plus 65 minus 65 090 and like that. And suppose Alice at rectilinear basis, Alice has got 90-degree, that is vertically polarized light, and again here also it has got vertically polarized light, so it has assigned 1, and then this will come as 1 as a key raw key bit. Here the basis has not matched. 60 Alice has chosen 67, Bob has chosen 45, so this will go for Bell testing. Here also 090 is chosen, but here also this is not matching because Bob has chosen diagonal basis, so basis mismatch. Here they have chosen again the same basis, so they will generate the keys because it's at Alice has received a horizontally polarized light or 0, so that's why they had assigned 0. So only 2 columns they are matching, and remaining all are going for Bell test. Okay, so that's how this system works. Okay. So here the key rate will be less because the matching probability is very less. Earlier it was 50% probability. Now it has reduced because out of these three, only 090 is contributing to generation of keys. So the key rate in E91 protocol will be less compared to BBM92, but it is more secure in the sense that we are validating the entangled source. So if the entangled source is not true, immediately the Bell parameter will deviate from its actual value. Then we can know that entanglement source that is there entangled, it is not generating properly entangled, maximally entangled pair, or it is not properly entangled. So we can have a check on the source as well. So that's how the E91 protocol is considered more secure. So here you can see that only key is being generated only when the bases are matching 090 rectilinear basis. In all other cases are going for Bell test. Okay, is it okay, or any doubt? Please let me know. Yeah, okay. Okay, so this is a simple representation of the Alice and Bob setup in E91 protocol. So here you can see that I told you that in Alice there are three bases: 22.5, 67.5, and rectilinear basis 090. And in Bob there are two bases: 090 and 45 minus 45. So you can see that we have an entanglement photon source here that is generating HH plus VV pair. So to check in the rectilinear basis, this part of the Alice will be used. Then for there is a polarization rotator here. Then this will be used for checking the another degree of freedom, like another basis that may be, say, for example, 22.5. Then another polarization rotator is there, and if the clicks are there, that will be used for the other that is 67.5. So this halfway plate is basically HWP, or the halfway plate is basically a polarization rotator. It is acting as the polarization rotator. So, and this is the beam splitter, so this will split the light in a 50-50 ratio. So sometimes the light will come here, sometimes the light will go here, and if it comes here, it can be clicked at here, this detector, or at this detector. So the role of PBS is that if it will split the light into vertically polarized component. So if a single photon comes, it can go either in this direction or it can go in this direction, depending on its polarization and its probability. In the Bob, we had only two the polarization setting: rectilinear 090 and 45 minus 45. So this section is responsible for 090, and this section there is a polarization rotator here, and this will be responsible for the 45 minus 45 things. Okay, so the halfway plate is working as a polarization rotator, or it is helping to choose the measurement basis. And this first 090 do not need to be rotated, so that is that's why there is no polarization rotator in this for detecting the 090. So this section of Alice, and this section of Bob will contribute to generation of secure keys, and the other parts will contribute to checking the Bell parameter. Okay, that is determining the S. So this is a bit complicated system because there are 6 detectors in Alice and 4 detectors in Bob, but that's why it is more complex and more costly system. But the thing is that here the security is utmost because we are very this first of thing is that it is an entangled based protocol, And the second thing is that here we are also verifying the authenticity of the source through the bell test. So this is an experimental comparison of different implementations of this BBM 92 and E91 protocols. So you can see that for BBM 92 protocol in free space, they have one was done for 35-meter distance. It was around 2.33 kbps. Then another implementation for 200 meters, it was around 1.71 kbps secure key rate. And you can see that for E91, the secure key rate drops to around 200 bps. It was done on free space or for 1.5 kilometer. And one fiber based implementation of BBM 92 is also there, that is over 100 kilometer of fiber, that is giving around zero point 0.6 bps of secure key rate. So the secure key rate is less for these entangle based protocols, because in 100 kilometer coherent one way or DPS will give around 1 kbps or 2 kbps rate of key generation, but here this key generation is significantly lower, but we have a more security here. So we need to have a trade off between the secure key rate and the security. But it is also on the other hand, it is also a very on the other hand, it is also very complex to implement, because we are having so many detectors, and this we need to control this polarization and all these things. So that's how these things are there. So there is a quick comparison between these two protocols, BBM 92 and E91. So BBM 92 has a higher key rate, as I told earlier. E91 has a lower key rate. BBM 92 does not perform the bail tests, so it is less secure than E91, but E91 performs these tests and makes sure that the source is checked. So it is more straightforward, but it is more resource intensive. You can see from the diagram itself. So in BBM 92, we have assumed that the Charlie has a calibrated photon source, and but in 91 we are actually verifying the source. So the restriction on source is less, and it can be done for long distance communication, and but it is tougher for long distance communication because the probability of matching the basis is very less. So the key rate will be severely low for E91. So it is not much suitable for long distance QKD. Okay. So just let me know if there is any doubt regarding BBM 92 or E91. So these are the benefits and challenges, like we have getting better security, there is no chance of eavesdropping, and there is a concept called device independent QKD, where you do not need to trust any device. Okay, so this is a this leads to path to the device independent QKD, but it is also the challenge is that it is sensitive to noise, like other protocols as well, and we need a good quality entangled photon source, and we need to have a stable and efficient detector, because the probability of matching is very less, so we need to decode as much as possible. So that we need very efficient detectors, and most of the time SNSPD is used because that is having a very high efficiency. Okay, so I'll cover some slides on QKD networks. Before going that, if you have any doubt on entanglement system, please let me know. Yeah, I think some queries there. Okay, someone is telling that one basic doubt is that in key generation, for example, using QRNG, one random key is generated. No, actually, said the concept is that uh, QRNG is not generating a key. Okay, first you understand that QRNG is not generating a key. QRNG is generating a random data. Then we are modulating it in either say phase for DPS protocol, in time being for coherent one-way protocol, or in polarization for BB84 protocol. Then this state, this quantum state after this modulation is sent to Bob. Okay. Now during this sending to Bob, it may reach to Bob, or it may get absorbed in the channel. It may get dropped in the channel. So we are considering only those state that is actually receiving the Bob. So if Bob has not received anything, that is not being considered in the latter stage. Only the qubits that is received by Bob, that is considered. So that's why Alice is storing its values. So for suppose at T0 Alice is sending 0 and T1 it is sending 1, but T0 value is not reaching to Bob. So it will discard the T0 value in the during the post processing. So the post processing will start only the values that has been received by Bob. So at any time, Alice and Bob will know each other that which state has been reached to Bob. So that's how the things work. So if something gets dropped in the channel due to the loss, that does not rise to any issue at all. We are considering only the states that is received by Bob. So that's why I told you earlier that we are sending some quantum states through the quantum channel to Bob, and based on that received quantum state, these keys are being generated. We are not sending the keys in its raw form through the quantum channel. We are sending some quantum states. If the quantum state is received at Bob, then only we will start the key generation process. Okay. So what is the real-time applications of prepare and measure and entanglement protocols? These both of these protocols are used. Prepare and measure are widely deployed nowadays because they are very easy to implement, and they are very cost effective also. But entanglement protocol, as I told, it is more secure. People are working on it, but there are very limited deployment as of now. Some entanglement networks are there, but it is less compared to prepare and measure as of now. But people are working on having high quality entanglement sources, and they are trying, as part of the NQM also, they are trying to have a entanglement based QKT networks. Okay, so in future we will see deployment of both prepare and measure and entanglement based protocol. So entanglement protocol will be more complex, more costly, but it will always have a higher security compared to prepare and measure based protocols. So both will be there. So both have its own upsides and downsides. Prepare and measure is less costly, more easy to deploy. It supports longer distance, and on the other hand, entanglement space will be more costly, more complex, but it will have more security. Okay, that's how both will be both will be deployed. So it is being planned under NQM. Entanglement networks are being planned under NQM. Not presently, as per my knowledge, it is not there at present. So far, my knowledge is concerned. If I am not wrong, it is not there at present. But people are working to make it work for the entanglement network. Okay. So now, going forward, I'll just conclude this session using some overview of the QKD networks. So till now we are considering only the point-to-point QKD network. Now it might happen that always the point-to-point network is not sufficient, so there will be trusted relay, and there will be optical splitting or switching in between. So we need to form a network of QKD links. Okay, so this QKD network then will need to have a scale that should be secure, that should be scalable, that should be stable over time, that should be interoperable among multiple vendors, and they should be manageable. So that is the purpose of any network. If the network does not satisfy any of these parameters, then it will be very difficult to deploy or maintain such type of networks. So keeping in mind that this QKD will be deployed in a network fashion in future, so ITUT come up with the standards ITUT 3 Y.3800 series, and in that standard they have mentioned some layers of the QKD network implementations. So the basic physical layer is the quantum layer. In that layer we have this Alice and Bob nodes. They are connected using the QKD link, that is the quantum channel plus classical channel. So here this is an example of 3 node quantum system. So quantum A, node A can be an Alice, node B can be Alice plus Bob, and node C is again Alice. So that's why this system it will be Bob, because Alice, Bob, Alice, and Bob. So that's how these links are connected. So in the physical layer we have the quantum layer, and on top of it we have a key management layer. So this key role of this key management layer is that it is basically taking the keys from the QKD modules, then it is maintaining this life cycle, because once a key is supplied to an application entity, we need to delete the keys, because one key cannot be supplied multiple times. That will be a security issue. So it is responsible for the key life cycle management, and on top of that we have a QKD and control layer, and all these 3 layers are being monitored by a QKD network management layer. Okay, and you can see that there is a red line that is called the security demarcation. So this security demarcation states that while you are dealing with QKD systems, you should only be worried about the security of your key till the time it is within your below this line. So if you are working on a QKD system, you need to secure your quantum layer, key management layer, and QKD control layer, and QKD and management layer. But if the key leaves your system and it is supplied to some any service layer or any application entities, and the key gets compromised here, because it may happen that your QKD system is secure and your the key gets compromised by the root encryptor. So it is not actually the fault of the QKD system, but it is a fault of the application link. So that's why this demarcation is there. So while implementing a QKD system, we need to implement these layers in a and this ITUT has formalized that what are the functions of different layer. For example, you can see that quantum layer is responsible for generation of the quantum keys, Then key management layer is, as I told, is supports the key lifecycle management. It stores, formats, and distributes the keys on request. Then on top of it, we have the QKD control layer that manages the routing, sessions, authentication type of thing. Then we have the QKD network management layer that monitors overall performance and set up the FCAPs. FCAPs means fault account configuration, accounting, performance, and security. Okay, so it manages the overall network. And then we have the service layer and the user network management layer. So the service layer is basically your application layer where the encryption or decryption is taking place. So this encryptor or this router is placing here. So it will request the key from the key management layer, and the key will be supplied through an interface. And once the key leaves your QKD system, then it is the responsibility of the service layer to maintain the secrecy of the key. So that's why the security demarcation comes into picture. Okay, we need to below this line we need to maintain the security, and it is not our responsibility actually to maintain the security of the application layer. It is someone else's responsibility to maintain the security of the application or the service layer. So this is taken from ITUT Y.3800 series. So this standard is freely available. If you are interested, you can go in depth in the standards. They are written in very lucid language, and it will give you an idea how the quantum network, QKD network, will be deployed or it will be developed. Okay, and they have defined some types of QKD networks. So there are three types basically. So these types are very simple because they define only the how the relay nodes are placed. So as I told yesterday, that due to the fiber loss, the distance, there is a distance limitation, and we need to have key relay in between. So in QKD network type 1, you can see that here between A and D there are two key relays. But in the user network, they are directly connected because there you can put optical amplifiers or like that. So this link can be long enough so that it can go from A to D directly. Similarly, in case of type 2 network, the number of relays in quantum layer in the user network, they are identical. So here are two relays in quantum layer, and the two relays are in there in the user network. Okay, so there are symmetric number of relays in both the user network and the quantum layer. Similarly, here the type 3 user network, there are differential type of relays. So in here we have two relay nodes, and here we have only one relay nodes. So all these three combination is possible. So they have described it as type 1, type 2, and type 3 QKD networks. So based on your requirement or based on the ability of fiber, any type of QKD network can be deployed. Okay, so that's all from my side. So if you have any query, then we can take that, or I have a small quiz also. If you are interested, I can share the link. So I ask Professor Sir, Rajendra Sir, if
Probably
it is
you
okay.
can send me the questions. We'll be consolidating all the quiz questions at the end of the week.
Okay, that is okay. Okay, that is will be okay.
So you can
That is
share the quiz with me. I'll be putting the quiz together with the other sessions, and then
okay.
I
Okay.
mean the participants will be attending those questions.
Okay, okay. So someone is asking for my email ID. So my email ID I can write here. Yeah. So and if there is any query, just let me know. I think we have 5 more minutes left.
There is one question probably you can answer quickly. Is CDOT working on drone-based QKD?
Actually, at present we are not working, but we have signed a MOU with a startup to develop drone-based QKD. But we are yet to start that actual activity. We are in the very initial stage as of now.
All right.
We are
Okay.
mainly as of now we are mainly focused in the fiber-based QKD. All our systems are fiber-based QKD.
So there is
So
a
that
follow-up
yes,
question that is it useful? Drone-based QKD, is it useful?
yeah, drone-based QKD is useful. I don't say it is not useful. It is useful, no doubt, because the advantage is that if there is any some area where you cannot lay fiber and you need an some ad hoc network type of thing. Suppose there is an war-like situation and you need an ad hoc secure network. So that's why you can fly the drone there, and you can immediately establish a secure link to using the QKD and using the drone. So that is beneficial, but on the other hand, the thing is that we need to take care of the drone security as well, because someone might attack your drone itself. So that will impair your link. So that type of issue is there, but and the challenge is also there because drone is a moving platform. So we need to have the precise pointing, acquisition, and tracking between the drone and the ground station. So that is another challenge of establishing a secure link, because free space link is one challenge, but drone is a moving platform. So that is another challenge. So that's why it is very difficult to implement, but It has very good use case in some strategic sectors, but not for civilian use.
There is one more question, which is satellite-based communication in future drastically changes due to quantum computing technologies.
Yes,
Isn't
satellite based. I think China has already developed the two satellites. One of them is called Messias. So they are doing over, I think, more than 1,000 kilometers range. But the thing is that satellite QKD, as of now, it is only limited to night time of operations, because at daytime, due to the solar noise, you cannot operate much. And the satellite is coming over your head for only 10 to 12 minutes. Okay, because it's a low Earth orbit satellite. So within that 10 to 12 minutes of time, you need to log the satellite, you need to have a precise tracking, and then you need to generate the keys. Okay, so satellite QKD has definitely advantage because it do not require fiber, it supports long distance. But only issue is that you cannot have a satellite ground station at a city. You cannot have it in Delhi, you cannot have it in Jaipur, because there is a very high light pollution is there. So we need to have a in a isolated area, in a hilly area, we need to place the ground station there, and from that ground station to actually to the city, we need to have a fiber based QKD. So satellite QKD is suitable for long distance application, but it can alone, it cannot serve much purpose. So we need to have fiber plus satellite together.
somebody is asking about ISRO's satellite-based QKD?
Yeah, ISRO as part of the NQM, they are working, but I am not aware of the latest happenings from them in detail. But as per the NQM mandate, if you see the NQM document, there is a mandate to develop satellite-based QKD, and ISRO is working on that as in the NQM. But I am not aware of the present status of that, which how far they have reached.
All right. Thank you. Thank you very much for your informative session. And as you have already seen that participants have been interacting very much. And thank you for patiently answering all of their queries. And thank you for taking your time for this FDP. And we hope to see you as an expert speaker in coming future FDPs also. Thank you very
Okay,
much.
thank you, sir. Thank you. If you have any query, you can email me. I have shared my email ID. And I think
Yes.
this, yeah, okay, so I'll be happy to
Yeah,
answer
so
any
any
query.
queries, I mean, remaining queries can be addressed through his email, which is shared in the chat window. And thank you all.
Okay, okay, thank you for your time. Okay.